Hello, I'm Neeraj. Today I will try to explain some advancements in the transformer based architecture. Actually, these days transformers are used as a core technique in a lot of different NLP based models. Transformer generally contains two different parts, encoder parts and decoder parts. Bird and all its variants like Albert, Robert, and Distilbert, all those variants are using the encoder part of the transformer architecture. Similarly, GPT kind of models, which are very famous for natural language generation, actually using the decoder part of the transformer architecture. Similarly, XLNet kind of architecture. XLNet is a famous autoregressive language model. It uses transformer XL architecture as a background architecture. I have prepared one video on XLNet also. You can find it in my video list. Even for basic transformer architecture, I have prepared one video lecture. So you can find there I have discussed the core concepts about the transformer based architecture. So this is not the end. Means you find that even in the transformer there are a lot of varieties are available, like long former, transformer XL architecture, lightweight transformer. But when you say lightweight transformer, you will see that it started compromising with the quality. So this is the issue. Now again, if you go through some other uses of transformer architecture, then you will find that people started using transformer inside RNN to enhance the feature of RNN, that is called Transformer-to-RNN. Even I had prepared the video tutorial on that. This is very interesting, like how transformer can enhance the feature of RNN. Similarly, people started using transformer inside CNN. Even for graph neural network, transformer based graph neural network architectures are available. Even multiple such architectures are available. Because there are some barriers or issues in the graph neural network based architecture, people try to solve it through transformer based architectures. But I found that scalability is the major issue in the transformer based architecture. So I found one of the latest paper very interesting, like transformer quality in the linear time, like written by some Cornell University and Google research people. So I found some of the contributions from this paper very interesting. So I have gone through this paper this weekend and I decided to share it with you through a very small video tutorials. I hope that you will like this. So the major contribution as I got in this paper, or as I understand in this paper, is they have targeted multi-head self-attention architecture of the transformer architecture, and they replaced the multi-head self-attention architecture by their own proposed gated attention unit architecture and mixed chunk attention architecture. And after that, they have shown that how the use of these two contributions helps in reducing the time complexity, increasing the speed of the transformer architecture without compromising the quality of the transformer output with respect to the traditional transformer or vanilla transformer, which uses the multi-head self-attention architecture. So in this discussion, I will just cover the gated attention unit and mixed chunk attention. Now, to understand the concept of gated attention unit, we have to go through the concept of gated linear unit. Actually, in this paper, authors have taken the reference of Shazeer 2020 for gated linear unit. So we will go through that paper's references, like how they had explained the gated linear unit. So suppose we have some input like that. I have just taken two input like x1 and x2, and then I have just two neurons ANN and two dense layer ANNs here. Now this is one sharing to one of the dense layer and then sharing to another of the dense layer. Now we will have two dense layer. So what will be the output? Suppose it is like W1, it is like W2, it is like W1 dash, it is like W2 dash. So what will be the output in this case? The traditional output, if you just consider that we have a deep neural network, multi-layer perceptron dense layer architecture, then we just apply some non-linearity and then apply some Wx, it means weight of input into weight of neurons, and then we take some bias factor like that. And then here we can also say that it is like W1, X1, W2, X2, dot dot dot, and then B. And sorry, not dot dot, because we have just two. And now here it will create the difference. Here there will be no non-linearity. It will be just like W1 dash X1 plus W1 dash W2 dash X2, and then our bias, here it is our bias, this is also bias. Here there is no non-linearity. So this non-linearity we generally add with all neural network architecture to control or to get some min max threshold for the entire inside value. But here it is present and here it is not present. Means for the first dense layer output we can scale it or scale down the value to some level, but here we cannot do the same. Now the next part is, if we take the pointwise multiplication, so in that case we can apply the pointwise multiplication only if our this non-linearity is applicable directly to each of the elements only. Means we are not taking the entire sum. So here this non-linearity is different from the traditional, it is element wise. Element wise non-linearity. When we apply element wise non-linearity, means this is a part of those elements, then we can easily apply the pointwise multiplication. So once we get the pointwise multiplication, suppose we say it like U, we say it like B, then we can get some value here. Now suppose we add another dense layer here, then again we will have some output and weight like W dash 0, sorry, WO, W1O, W2O, like that. So in that case we apply this part is x, because this is the input. This is actually, this will work like input to the next dense layer output. So this input will work like x. So this input, we multiply this input to all those neurons weights connected to the third dense layer, and then we can get the output in this format. Now again, for flexibility, to apply this output separately for some other purpose, we will add the non-linearity function here. That will be again element wise non-linearity. So this is the difference. Now you may assume that this multiplication, pointwise multiplication, will create some representations, because with one we have some pointwise non-linearity, with other we don't have any pointwise non-linearity. So when we apply pointwise multiplication, we will get some representations that we can enhance through some another dense layer, and we use that output. And in some other research references, it is found that it is useful. Now authors also given the similar kind of explanations for the gated linear unit. So here the bias factor I have taken, but it is not present here. It is like pointwise non-linearity with this dense layer, pointwise non-linearity with another dense layer. Now other concept is x and w. So x is our input and w is the associated neuron weight. So this way this output is computed. Now for v, x is the another same set of input that we have shared. wv is another associated set of neurons, and this is another pointwise non-linearity. This pointwise non-linearity and this pointwise non-linearity is different. In the traditional explanations by Shazeer et al. 2020, in first case they have used sigmoid as a non-linearity, and in second case they have taken just a default value like 1 in place of this 5e value. But you can do the experiments with different type of non-linearity like RELU, RELU square, or any other things here. Now once you get the pointwise multiplications, you will have output in the format of like this. So this format of output is like a x. Again there will, once you connect this through some final output layer neuron, you will have some connectivities that will have some weight. So you have to multiply it through some weight. And in the final output layer, the authors didn't take any non-linearity. They just computed the output like that. Now that for the dimension purpose, they have identified the dimensions like for u and v, the dimensions will be like real of size t into e. So t will be the total number of tokens, and e is some intermediate size, depends upon the number of hidden layers or nodes that you define in the network. Similarly, here for output, they have taken the size real of size t into d, where d is the model size. So now it is clear that due to the presence of either different types of nonlinearity, element-wise nonlinearity, or presence and absence of nonlinearity can create some representations, meaningful representations for NLP related applications. That is one of the key input, and that is extended to achieve the gated attention unit. Now we will try to understand that how gated attention unit is actually implemented. So in the gated attention unit, I have just used the pseudocode given in the paper. I have just used the pseudocode given in the paper here. So from this pseudocode, it is clear that authors have introduced two different concepts here. First is relative positional bias. Generally, what happens in the traditional transformer architecture, we provide the positional encoding from beforehand, and it is going with the data or tokens in the system. But in the case of relative positional bias, it makes the model to learn the relative positions between the text. Means it replaces the traditional encoding, forced or encoding which comes with initials, to learning the distance between the token, relative distance between the token, to get some advancement over the traditional transformer architecture. So this is the relative positional bias. So it is very important. Second important point is RELU square. Uh, in the traditional deep learning architecture, you may have seen that some people used RELU cube also. But try to understand how RELU square is actually working. Suppose we already know that this is our negative side, positive, y positive side, x positive side, x negative side. So for all negative values, it shows the value 0, and for positive values, it shows some means non-linearity. But in the case of ReLU square, for all values less than 0 also, it will show some convergence, or sorry, it will show some non-linearity. Means instead of this phase, it will converge smoothly, means system will smoothly converge. That's why people prefer to use ReLU square in the NLP based applications. Now let us try to understand the rest of the parts, like how gated attention unit actually work. So first of all, the first part is to take the scale offset and values, like how we take the input and just make some offset calculations and other things. So no need to explain this part. This part is important. The next part is, after getting the value for the dense layers, as written here, like z equal to dense x and s. Now we provide the scale offset through this way. So scale offset is like we are just changing the shape and adding that shape related informations with the data, and then we get the scale offset in the form of query and key value. So this part of getting the query and key value is very much similar to that we are using in the case of multi-headed self-attention. So what we do in the multi-head self-attention, the concept of query and key is very much similar to our concept of searching something by using some keywords and when we fire those keywords, we try to match it with the saved indexes, and based on that matching we try to identify things. So similar to the concept of multi-head self-attention, the concept of query and key is considered here. Now here you can see that QK, so query and key value, the multiplication of query and key value is taken here like we do in our multi-headed self-attention architecture. I have used the Vaswani's general paper here. So what they do, it takes the query and then key and then apply math multiplication. So same Einstein sum, that is actually the matrix multiplication that multiply this matrix with this matrix and store it into this matrix. So same kind of math multiplications value between query and key is like that. In the previous tutorial I have already discussed, for example, suppose we have some of our indexes like how are you, and we fire query like how are you with our indexes, then suppose it is again, then we get some value in the matrix here through the matrix multiplications. After that, here you can see that it is use the RELU square. In the traditional multi-head self-attention, what they do, they apply scaling and then masking, scaling to avoid the overfitting, and masking, actually masking generally they use with decoder in the multi-head self-attention architecture. Just watch my previous video. I have given the tutorial link in the description box to understand all those things in the detail. But after that, suppose we skip those things, and after that it calculates the softmax value. But here, instead of computation of softmax of those output, they are calculating the RELU square. Now this is the difference. So they are doing two different things. First is they are calculating the RELU square. This is our activation, and then QK is actually the math multiplication, and then plus relative positional bias. Between query token and key token. So This relative positional bias generally gives the information that what are the distances, relative distances between the tokens in key and query and key values. So this is very helpful according to the authors, and even it is proved in a lot of transformer based improvement papers that relative positional bias plays very important role. Now I have explained that how the RELU square function will behave. It will affect the convergence of the function. Now the next part is to multiply the stores this value as a. Now they take another value b and multiply it with that. Similar way, in a similar fashion, if you see this architecture, here also we take a value vector or value matrix based on the data shape and multiply it with the output of query and key output, softmax output. So the value matrix initially may be empty or may contain some initial value. So when multiply it with the query and key softmax output, in the current case RELU square output in place of softmax output, and then with the help of relative positional bias, so when we multiply it with b, it gives the some output that is our attention output. So according to this output will be our attention output. Now we take the pointwise multiplication of attention output with the starting dense output. Now here one more things that authors had considered in the third equation, if you see that they have used one shortcut connections. So there is a one shortcut and x, where shortcut is x and x is norm x. So I already discussed several times in the previous lecture regarding what is norm, how to calculate. Even in previous lecture I discussed, so just skipping that part. So once we have very much clear output. So this is our V output, this is considered as output U. So our U and V output will be, so U output is considered as dense X and E. So E is some intermediate shape of hidden layers that we try to design the architecture, because at the intermediate level of the network designing we generally contain some different number of neural networks nodes compared to the final output layer. So this is some intermediate layer size, and V is again after getting U and V, we take the multiplication of U and the attention that is coming through dense layer here. This is actually pointwise multiplication, like here, and then attention that we have calculated in this part, and after that we pass this to final dense layer. We pass this as a output to final dense layer, and this dense layer will contain the output equal to dense x. As I said, here the dimension will be d. And one more thing that they added, after or at the end of or at the final stage of gated attention unit, the authors are adding one shortcut. So that shortcut is actually x here, that you can see. So one shortcut will be added. So the significance of shortcut is to avoid, I think, vanishing gradient kind of things. So this is the way the gated attention unit is actually working. So the major differences I found that here in the multi-head self-attention, they are using the softmax, they are using pre-annotated or pre-calculated positional indexes, but here they are using RELU square instead of softmax. They are using relative positional bias instead of pre-calculated indexes or traditional bias. Now let us go through the mixed chunk attention. So the concept of mixed chunk attention will be easy to understand if you concentrate on this figure. Here, the first part, you can see that all the attention heads are connected to a single node and it repeats for all other nodes. So this is called quadratic kind of attention. Second is linear type of attention. Here you can see that how attention heads are indicating each others in a linear fashion. But here it is a mixed chunk attention. Here you can see that how the locally mixed chunk attentions are there. So the attention heads, how it points, and then you can see some cross connections also. So this is mixed chunk attention, local mixed chunk attention, that is actually proposed by authors. And here the chunk size equal to 2 taken by the authors. Here you can see that chunk size 2 is taken by the authors, and entire things achieved in a properly non-overlapping fashion. So according to the paper, in the concepts where they decided the mixed chunk attentions, so they divided the entire sequence into G non-overlapping chunks, and each chunk having size C number of tokens. So if T is the size of tokens, we can say that T equal to T by C into C. So such kind of relations can happen. Now due to this kind of arrangements, the system can return 4 different attention heads: quadratic attention heads and linear attention heads. So quadratic attention head for query and key inside the chunk, because here you can see that this is small chunk. So inside the chunk, same kind of quadratic attentions are possible. And similarly the linear attention, like one by one attention, like here we have achieved the linear attention, traditional linear attention that we achieved here. So 4 different attention heads in the form of query and Q value is actually returned by the mixed head attention system. Now the computation scheme is very simple because as we explained the gated attention unit, the mechanism is not changing. Mechanism is almost same. Now how to compute in this case of mixed chunk attention, how you can compute the global and linear both. So, when you want to compute the local attention per chunk, it is very much similar that we discussed with gated attention. You will use the RELU square activation function, and inside the local attention per chunk, so inside the local you can see that it is a quadratic kind of attention things. So here we achieve the quadratic attention by using ReLU square, query and Q multiply, then bias, and then VG. The entire arrangement is same like this. Only thing is that we will take 2 at a time. In the computation, or suppose here C equal to 2, but suppose C may be equal to 5 or something. So based on the chunk size, we will take the group, and based on the group, we will calculate the value part by taking this attention. Now the next part is global attention across the chunk. So there may be some global, like here you can see that across a particular node there are some global attention like this for this, for this, for this, for this. So we add all those such kind of attention that for related to key values, we just add all those attention values. So same kind of things in non-causal and causal arrangements they have achieved by adding the attention key value heads by taking it in the transpose position. Now let us try to get the final outcome. So final outcome is very much similar to this outcome. Here it takes the values that are coming in the chunk, then pointwise cross multiplication or pointwise multiplication, and then of sum of attentions in quadratic and linear form both, and the weight associated with the final dense layer neurons. So this is considered like a X part and this is weight part. So WX part that they achieve, and it will pass through the dense layer. So this is the case where the mixed chunk attention is achieved. So in the mixed chunk attention, the mixing they have made, like they had, instead of taking everything globally, they have created a small chunks, and then locally and globally they calculated the attention like the process applied in gated attention unit, and then they combined those attention and then calculated the final attention. So this is the mixed chunk attention process. So these are the two key contributions that I liked most in the paper. Maybe I missed some point in this paper or misunderstood some points in the paper, but I tried my best to understand this paper during this just 1 or 2 days weekend. So hope you will find the entire tutorial interesting or entire discussion interesting.